delta S, denoting the entropy change, is always greater than or equal to 0. This is the arrow of time formula, which defines the distinction between the past and the future. It stands alone in fundamental physics, serving as a beacon to guide our understanding of the passage of time. Within its confines lies the entire universe. This inequality is called the second principle of thermodynamics. Its essence is the unidirectional flow of heat from hot to cold bodies, and never in the opposite direction. The discovery of this principle is attributed to Ludwig Boltzmann, a romantic figure whose life was cut tragically short. This Austrian scientist was the first to try to unravel the mysterious essence behind this formula and lead us to an understanding of a profound anomaly. This anomaly, which can be observed simply by looking out the window, consumed all of Boltzmann's thoughts. He envisioned a universe of infinitesimally small atoms and set about his work with unwavering determination. Boltzmann's insights illuminated the behavior of gases, revealing their dynamics through the collective motion of molecules or atoms. This discovery gave Ludwig indirect evidence for the existence of atoms, but direct observation remained elusive. The lack of tangible evidence made him susceptible to criticism from his colleagues. However, it was not the skepticism of those around him that bothered him most. For years, he had been trying to unravel the origins of the physical order. Despite fruitful scientific endeavors, each attempt failed. The predictions of Ludwig's theory contradicted what he wanted to show, while his everyday experience reflected increasing order. Blossoming flowers, growing trees, a society undergoing industrialization. His theory predicted the disappearance, not the increase, of order. He explained phenomena such as hot bodies, cooling, coffee dissolving in water, and birdsong dissipating in the wind, illustrating how the microstructures of the universe devolve into chaos, destroying order. The order around him made Ludwig deeply uneasy. He felt there was a missing element in his theory, but could not identify it. In 1906, exhausted by his relentless search for answers, Ludwig tragically took his own life. His body, composed of atoms, began a gradual and inevitable decay that reflected the predictions of his theory. The 20th century confirmed Boltzmann's beliefs about atoms and partly justified his desire for interdisciplinary research. The emergence of quantum mechanics, molecular biology, biochemistry, and evolutionary theory helped to bring different scientific fields closer together. Beyond these interconnections, however, a unifying concept permeated all fields of knowledge. The concept of information fascinated and puzzled Boltzmann. In the 20th century, the study of information became widespread, spurred not only by the fascination of the elegance of nature, but also by the grim realities of warfare. The need to secure communications during World War II prompted the application of mathematical methods to the study of information. Encrypting and decrypting messages presented serious mathematical puzzles. Pioneers in the field, such as Claude Shannon, Warren Weaver, Alan Turing, and Norbert Wiener, became known as the first cyberneticians. In the 1950s and 1960s, the concept of information swept the scientific community. Information transcended scales, being neither limited to the microscopic nor macroscopic realm. It could be written on clay tablets or intricately woven into strands of DNA. The scale independence of information has made it attractive to researchers from a variety of disciplines. Biologists studied the encoding of hereditary information in genes, and engineers developed communication technologies. Engineers invented communication devices. Computer scientists, psychologists, and linguists modeled the brain with electronic thinking machines. Despite its growing popularity, the tangible nature of information, a problem that resonated with Boltzmann, gradually faded into oblivion. The term information has become synonymous with the intangible and the digital, relegating its physical nature to the periphery. But information has a physical nature, just like atoms or the energy of their motion. Unlike solids or liquids, it does not have individual particles, but it has a physical nature, like motion and temperature. Information is a form of physical order. In 1949, Claude Shannon and Warren Weaver published The Mathematical Theory of Communication, a seminal work that laid the foundation for what is now known as information theory. To fully understand this theory, They needed to separate the term information from its colloquial connotations, particularly its association with meaning. This separation was driven by both technical and philosophical considerations. From a technical point of view, Shannon sought to develop machines capable of transmitting information, devoid of any inherent meaning in the message. From a philosophical point of view, the authors recognized the inconsistency between information and meaning. While humans can endow information with meaning, what passes through the wires is simply raw information, devoid of contextual meaning. For example, the phrase September 11 may evoke different associations for Americans and Chileans, emphasizing that meaning is subjective and context-dependent. Perceptual purity does not equate meaning and information. Claude Shannon sought to create a machine that conveyed information independent of meaning by developing a formula to determine the minimum number of characters needed to effectively encode a message. This formula coincided with Boltzmann's entropy formula, revealing the inextricable link between information and entropy. This coincidence emphasizes the physical nature of information and its relationship to the fundamental principle of thermodynamics. The physical nature of information, confirmed by the coincidence of the Shannon and Boltzmann formulas, plays a key role in understanding how the study of atoms can help make sense of humanity's technological progress. In this video, inspired by Cesar Hidalgo's book, Why Information Grows, we explore the mechanisms of information diffusion at various scales, from atoms to civilizations. We will look at the history of the universe from the perspective of the arrow of complexity rather than the arrow of time, emphasizing how the growth of information shapes the history of the cosmos and intelligent beings. After the Big Bang, the universe tends toward disorder, increasing entropy, but at the same time, pockets of physical order, such as planet Earth, emerge. Over billions of years, the Earth has seen a steady increase in information, becoming a sanctuary of bubbling knowledge, fueled by solar energy and the self-replicating mechanisms of biological evolution. All that fascinates me. Ludwig Boltzmann, and you represents physical order or information, the dense complexity that greets us every time we open our eyes. This richness exists not only because information pervades the universe, but also because we emerge from it and actively participate in its creation. In this video, we will attempt to make sense of Boltzmann's question by examining an anomaly. Why does the increase in entropy in the universe coincide with the inexorable expansion of information? We will explore how the spread of disorder and chaos is intertwined with the emergence of complexity and organization, exemplified by life. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. You may not remember, but a few decades ago, you traveled through time. You were born. During your labor, you traveled a span of 100,000 years, moving from the ancient confines of your mother's womb to a complex modern technological society. While you were in your mother's womb, the environment was similar to that in which infants lived millennia ago. However, the moment you were born, everything changed. For children born in the 20th or 21st century, the experience is vastly different from that of earlier generations. Our contemporary world is characterized by a proliferation of tangible items, cars, lamps, clothing, and appliances that once only existed as concepts. Yet, what truly defines modernity is not the mere existence of these objects, but rather the manner in which matter is arranged, the physical order that embodies information. While it may seem evident that objects embody information and imagination, it's crucial to recognize that information is an intrinsic aspect of nature, predating the emergence of life itself. As life evolved, the accumulation of information accelerated, notably through the replication of DNA and RNA molecules. Living organisms are intricately organized entities that both process and generate information. What distinguishes humans, however, is their capacity to externalize vast amounts of information beyond their physical bodies. This is evident not only in books, records, digital files, but also in the artifacts and creations that populate our world. From primitive tools like arrows and stone axes to cutting-edge technologies like quantum computers and the internet, Our ability to manifest the objects conceived in our minds sets us apart from other species constrained by the limits of nature. Consider, for instance, the Bugatti Veyron, one of the most luxurious cars in existence. The Bugatti Veyron is worth approximately $2.5 million. By comparing the value of 1 kilogram, approximately $1,300, to the price of gold and silver, we can see its exceptional value. While the value of a kilogram of an average car typically ranges from $10 to $60, the Bugatti Veyron surpasses even the value of an equivalent weight in silver. Conversely, a car like the Hyundai Verna can match the value of its weight in bronze. While comparing the weight of a luxury car to precious metals may seem meaningless, it emphasizes how physical order or information is encapsulated in the product. Imagine you won the lottery and received a Bugatti Veyron, and on your first day you inadvertently crash into a wall. Your health is fine, but the car is beyond repair. What happened to its value? In an instant, the monetary value of the car disappears while its physical weight remains unchanged. This is not because the accident has destroyed the atoms that make up the car. Rather, it has changed their arrangement. The separation and deformation of the car's components largely destroyed the information embedded in the Bugatti. Simply put, the value of the car was not determined by the intrinsic value of its atoms, but by how those atoms were organized. This organization of atoms represents the essence of information. Claude Shannon, often regarded as the father of information theory, defined information as the measure of the minimum data necessary to transmit a message. This concept extends to various contexts, including the organization of complex structures, like the atoms comprising a Bugatti car. To grasp Shannon's notion of information, let's begin with a simpler example, a classic tweet consisting of 140 characters. Similar to a Bugatti, a tweet serves as a concise packet of information crafted for communication. Yet, according to Shannon's theory, the tweet's intended message holds no significance. Information, in this context, refers solely to the minimum data required to convey any message, regardless of its content. To quantify the content of a tweet, consider a hypothetical game. You must guess a friend's tweet, using only yes or no questions. Armed with a book containing all possible tweets, the game commences as your friend randomly selects one from the book, and you attempt to decipher it through a series of yes or no inquiries. Shannon's doctrine states that the amount of information in a tweet is equal to the minimum number of questions needed to accurately guess the tweet. So what is that number? For simplicity, let's assume that you use an alphabet of 32 characters to write tweets, and you have a table in which each character has a sequential number. To effectively guess a friend's tweet, you would use questions, gradually halving the search space of possible tweets, character by character. For example, an initial question might be, is the number corresponding to the first character greater than 16? If the answer is negative, then the first symbol lies between A and P. Then the second question might be, is the number corresponding to the first symbol greater than 8? A positive answer means that the first character lies between I and P. This process continues, each question having the number of possible characters until the tweet is decoded. With 32 possible characters, 5 questions are enough to guess each character. Thus, a tweet 140 characters long requires 700 yes-no questions, or, in the language of information theory, 700 bits. Shannon's theory serves as the cornerstone of modern communication systems. By determining the number of bits needed to encode messages, Shannon helped develop digital communication technologies. He called his measure entropy, following the advice of John von Neumann, as his formula echoes the entropy formula in statistical physics developed by Boltzmann nearly 50 years earlier. Nevertheless, reconciling Shannon's and Boltzmann's interpretations of entropy and information proves to be a difficult task. For example, according to Shannon, if you randomly shuffle all the bits on your computer's hard disk, which erases all your photos, documents, and files, this action will increase the amount of information. Indeed, transmitting a message about the state of a disk with random data requires more bits than conveying information about a disk containing photos and documents. This discrepancy arises because the latter often exhibits patterns and correlations that facilitate compressions. Boltzmann's concept of entropy diverges from the common notion of disorder. Rather, it signifies the array of equivalent states. Consider your clothes closet. Boltzmann's entropy represents the multitude of configurations in which items can be arranged on the shelves. Typically, there are more disorderly arrangements than orderly ones. But if you suddenly have a second closet that is exactly the same, entropy will increase. After all, things can now be arranged in even more ways, although the clutter won't get any bigger. Thus, in Shannon's language, the concepts of information and entropy are functionally equivalent, since the number of bits needed to create a message is a function of the number of possible messages that can be transmitted, Cesar Hidalgo. But that doesn't make entropy and information the same thing. As Nobel Prize-winning chemist Manfred Eigen observed, entropy refers to an average physical state, while information refers to a particular physical state. Going back to the Bugatti example, a car is a much more complex design than a simple tweet. It involves a particular arrangement of a huge number of atoms, not just 140 characters. We are not interested in every possible configuration of atoms, but one that exactly replicates the Bugatti car. For example, changing the arrangement of the tires changes the arrangement of the atoms, but retains the basic properties of the car. Thus, Bugatti with a changed tire arrangement are considered identical. The group of Bugatti in running condition is relatively small. The group of broken Bugatti includes more states and higher entropy. Consequently, more bits are required to transmit a message about broken Bugatti despite their lower information content. However, the largest group is Bugatti in the form of iron ore and other chemical elements. The complete disassembly of Bugatti into its constituent elements destroys information, while the act of reassembling Bugatti embodies it. This example emphasizes the rarity and complexity of configurations of matter that encapsulate information. The problem is that systems are not free to move from one state to any other. The existing order of matter limits the possible transformations, and moving from disorder to order requires many successive steps. There are far fewer paths from disorder to order than there are backwards. Therefore, if you shake a box of alarm clock parts, it will take billions of years for the alarm clock to assemble itself. A Rubik's Cube provides a tangible demonstration of the correlation between available options and entropy, as it cannot be assembled randomly. With a staggering 43 quintillion possible states, only one represents perfect order. While the cube can always be arranged in 20 moves or fewer, finding the correct sequence of moves proves challenging. The basic solution method typically exceeds 50 moves. Consequently, only a handful of pathways lead to perfect order, rare among the multitude of chaotic possibilities. This principle extends to the universe itself. Information, ordered states, is exceptionally scarce. A similar level of orderliness is observable in living organisms, such as DNA molecules. The sequence of DNA nucleotides is not random. Comparing a genuine gene with a random nucleotide set reveals a discernible order, indicative of meaning within the gene. Such purposeful, informative DNA sequences could not arise by chance alone. They are the outcome of billions of years of evolution and natural selection. From countless random variations, nature has sifted, preserved, and refined those rare sequences that confer advantages upon organisms. Just as assembling a Rubik's Cube poses challenges for a child, creating ordered DNA sequences that convey information is no easy feat for nature. The definition of entropy, rooted in the multiplicity of states, is intertwined with the capacity to process information and perform calculations, thus linked to intelligence. You probably know the game where children learn to insert objects into the appropriate holes. At about 14 months of age, most children can easily handle spheres and cylinders, but have difficulty with cubes and polyhedrons. Placing a sphere is not difficult. It looks the same from any angle. Similarly, a cylinder is not particularly difficult because it remains unchanged as it rotates around an axis. However, a cube offers only a few rotations, and polyhedra offer even fewer. For a child, a triangle with unequal sides that has only one correct position presents a challenge akin to a Rubik's Cube. By playing, children learn to identify these rare, low-entropy states. Detecting these rare but valuable states provides a simplified model of intelligence. It's all intuitive. Now, let's delve into deeper questions. Where does information come from? And why is time irreversible? Together, these questions present a perplexing mystery. After all, time flows from order to disorder, and the complexity of our world is increasing. It turns out that the growth of entropy in the universe contradicts the growth of information. The irreversibility of time is a mechanism that creates order out of chaos. The desire to turn back time is shared by many, but time flows inexorably in one direction, from past to present, from youth to old age, from life to death. The irreversible nature of time has long puzzled mankind and cannot even be explained within the technical framework of Newtonian and Einsteinian theories of motion, which once allowed for the reversibility of time. But these theories could not explain why a wrecked automobile cannot spontaneously repair itself. The irreversibility of time is not just a curious feature of nature. It is closely related to the physical origin of information. Both phenomena depend on laws governing the behavior of large aggregations of particles. The coexistence of the irreversibility of time and the pervasiveness of information in the universe is a profound mystery. Time, irreversibility, is associated with the transition of the universe from order to disorder. However, on our planet, we observe the opposite trend, the constant growth of information. This realization came to physicists in the 19th century. Although the world is accelerating and becoming more complex, they realized Boltzmann's revelation. The sound of a guitar fades, and the ripples caused by a thrown stone dissipate as the pond returns to its calm state. This loss of information finds an explanation in physical laws discovered in the 19th century. The paradox associated with the increase in information became widespread when Charles Lyell and Charles Darwin challenged the biblical view of the age of the Earth, claiming billions of years. This discovery suggested that the anomalous increase in information observed over time had occurred over billions of years. However, anomalies cannot exist indefinitely, hence the logical conclusion that our understanding of nature is incomplete. Ludwig Boltzmann's seminal contribution in 1878 showed that systems composed of many particles gravitate toward states with minimal information, a principle embodied in the second law of thermodynamics. According to this law, the entropy of closed physical systems invariably increases. Let's consider a simple example. Let's drop paint into a glass of water. Initially, the system is saturated with information because there are only a few ways to localize the paint and many ways to distribute it evenly. Countless examples of increasing information and complexity can be found throughout the universe. However, the question remains, where does all this information come from? According to the theories of Boltzmann, Maxwell, Gibbs, and Einstein, the universe must evolve into a homogeneous, information-free state, devoid of free energy. In the 20th century, the understanding of the arrow of time and the physical origin of information were agreed upon. New theories showed that information is not an anomaly, but an expected phenomenon. A key thinker in this field was Ilya Prigogine, who received the 1977 Nobel Prize in Chemistry for his contributions to non-equilibrium thermodynamics, especially the theory of dissipative structures. He put forward the idea that information naturally arises in steady states of non-equilibrium physical systems. That sounds a bit cumbersome. So, to make it clearer, we need to deal with the idea of a steady state and understand the difference between two steady states, dynamic and static. Here's an example of a static, steady state. A ball thrown into a glass. We're all familiar with the result. Shortly after being thrown, the ball settles into a stable position at the bottom of the glass. Now, let's look at a more intriguing example of a dynamic steady state using a box filled with gas as an example. If we pump gas into one side of the box and let it equilibrate, eventually, the amount of gas in the right side will equal the amount of gas in the left side. However, the steady state of the gas is not analogous to a ball resting at the bottom of the glass. Instead, all the molecules of the gas in the box are in constant motion, and equilibrium is reached when the number of molecules moving from left to right is equal to the number of molecules moving from right to left. Thus, the box of gas is more like the example of a drop of paint in water. Now, let's look at the concept of steady state in a non-equilibrium system. A classic example of a non-equilibrium system is the whirlpool formed when water is drained from a bathtub. This vortex remains stable as long as water is present in the system and, remarkably, is information saturated. Vortices, such as whirlpools, are rare configurations of water molecules that do not occur spontaneously in standing water. Within a vortex, molecules move non-randomly, with each molecule having a velocity and trajectory that correlate with neighboring molecules. Similar examples of non-equilibrium systems are the curls of cigarette smoke, the motion of a campfire flame, the glow of a computer screen, and even you and your smartphone. Prigogine recognized that Boltzmann's theory could not fully explain the phenomena observed on Earth because our planet exists as a non-equilibrium pocket in a universe striving for equilibrium. The Earth has never approached a state of equilibrium. Rather, the energy from the Sun and nuclear decay in the Earth's core continually disrupt the equilibrium, providing the energy necessary for information to arise. In essence, the Earth is a small information vortex in the vast cosmos. Prigogine concluded that to understand the information-rich nature of the universe, it is necessary to understand the properties of non-equilibrium systems. He found that non-equilibrium systems differ from the properties of Boltzmann systems, which are usually composed of a large number of particles. In his work, he formulated mathematical laws and principles that clarified the behavior of non-equilibrium systems, showing that chaos hides information. Consider the heating of water in a pot. Initially, slight heating does not cause the organization to transition to an information-saturated state. However, prolonged heating leads to turbulence, and in this chaotic motion, information is hidden. After chaos, non-equilibrium systems often transition to highly organized states teeming with correlation and information. Let's take a closer look at boiling water in a pot. At first, the water heats up uniformly, representing an equilibrium state. However, further heating leads to the emergence of ordered structures, striking patterns and flows in which the water circulates in a directional manner. This phenomenon exemplifies self-organization in non-equilibrium systems, a concept revealed by Ilya Prigogine. Systems, far from equilibrium, of which there are most in nature, spontaneously generate order and organization. Thus, the emergence of ordered structures saturated with information on a non-equilibrium planet, like Earth, is not an anomaly, but a common phenomenon. However, any order struggles with entropy. Its eternal adversary, entropy forever, seeks to destroy ordered structures, so as soon as the heat source under the pot goes out, the beautiful patterns disappear completely. In the natural world, entropy is always poised to consume pockets of order, whenever conditions become even slightly unfavorable. However, information has developed mechanisms to preserve itself. One effective strategy is replication, spreading copies of its genetic material. I delved into this topic in the video From Atoms to Consciousness. What is life? Another fascinating method was uncovered by Prigogine. He demonstrated that non-equilibrium systems naturally progress to a steady state where entropy production is minimized. Essentially, these systems inherently select a developmental path that requires the least amount of energy to maintain order. This low-energy approach enhances the survival of information, just as boiling liquids form cell structures. Any non-equilibrium system seeks stable states, where the new order is as resilient as possible. In a way, the system functions like a rational entity opting for the best strategy for self-preservation. This intricate relationship between entropy, information, and the potential emergence of intelligence during the universe's evolution is profound. For those interested, there's a wealth of complexity in non-equilibrium statistical physics to explore. However, our primary focus in this video is to grasp the origin of information. Prigogine and Grégoire Nicolis, in a brilliant 1971 paper on the links between non-equilibrium systems and life, noted, generally speaking, the destruction of structures is a situation that prevails near the position of thermodynamic equilibrium. In contrast, the emergence of structures may occur with specific linear kinetic laws outside the stability region of states, characterized by ordinary thermodynamic behavior. In simple terms, in nature, balanced states often lead to collapse and disappearance. However, when equilibrium is disrupted and various processes take place, new and intriguing structures and forms can emerge that weren't present before. Imagine a jazz ensemble, improvising. When musicians play with passion, new melodies and harmonies are born. But this music exists only momentarily and vanishes if not recorded. Similarly, in physical systems, being far from equilibrium allows for the creation of new structures and patterns. But these are often fleeting due to their instability. By studying such systems, we gain insights into the fundamental origins of information, for information to persist over time, to be stable and evolve, essential for the emergence of life, mind, and culture. Additional stabilizing factors are necessary. Nobel Prize-winning physicist Erwin Schrödinger highlighted in his book, What is Life?, that the longevity of physically embodied information cannot be comprehended by examining only liquid systems. Elements like cigarette smoke, vortices, droplets, paint, and gas are examples of such liquid systems. Imagine creating a beautiful pattern with colorful pebbles on the beach. If the tide comes in, the waves will quickly destroy the pattern. But if you could instantly glue all the pebbles together into a solid panel, the pattern would endure for a long time and could be transported anywhere. Similarly, in nature, when information is embedded in something solid, structured, and stable, it can be preserved and transmitted far longer than in something fluid and changeable. This is why Schrödinger argued that solids are crucial for understanding life. Proteins and DNA molecules, which encode all the information of living organisms, are essentially periodic crystals, structures that do not repeat but contain extensive correlations. This crystalline structure makes them ideal carriers of information. Thus, by combining the ideas of Prigogine and Schrödinger, we can understand where information comes from and why it persists. The poetic quirk of this combination is that, according to it, our universe is both frozen and dynamic. Yet, the growth of information implies more than crystalline solids and dynamic whirlpools. For information to truly accumulate, the universe requires another trick. It is the information processing capacity of matter, that is, the ability of matter to do computation. Cesar Hidalgo. Consider a tree. Essentially, it's like a solar-powered computer. The tree responds to changes in daylight hours and adjusts its behavior according to the seasons. It sheds and grows leaves, directs its roots towards water sources, defends itself against pests, and more, constantly processing environmental information with complex molecules and proteins. A tree operates without consciousness or developed language, yet it processes information in its unique way. This ability arises from the tree being a stable structure within a non-equilibrium system. However, trees are living organisms, so we can't assert that the ability to process information or compute predates life. To explore this, we need to examine simpler systems, like chemical reactions. Imagine a series of chemical reactions transforming substances through intermediate states. With a constant influx of starting materials, the system initially reaches an equilibrium where these states form and decay at equal rates. Increasing the flow of starting substances disrupts this equilibrium, pushing the system into one of several new stable states. Essentially, the system chooses between these states. Further increasing the flow leads to the emergence of even more complex and ordered stable states, such as chemical clocks, compounds that periodically transform into one another. By adjusting the concentration of initial substances, we guide the system into different, steady states, effectively making it calculate different outcomes based on the input data. This resembles primitive metabolism, or even a cell altering its type. Thus, complex chemical systems can process information, indicating that the ability to compute along with information itself existed before life. Life emerged because matter had the capability to compute. Boltzmann struggled to understand why order in the universe increased rather than decreased as the second law of thermodynamics predicted. Life and mind, however, can accumulate information and create local order while accelerating the overall growth of entropy in the universe. As Erwin Schrödinger noted in What is Life? Life feeds on negative entropy, extracting it from the environment, and expelling positive entropy. This resolves the paradox. Life and mind accumulate information at the expense of increasing entropy around them. So what does all this have to do with the irreversibility of time that we started the conversation with? Imagine a lake covered with biodegradable marbles. Initially, the marbles are neatly arranged in trucks, but once released, they spread across the lake's surface. Can we reverse their movement, akin to reversing time, to return them to their original arrangement? Let's imagine two extraordinary machines. The first machine can instantly change the velocities of any number of marbles as commanded, but with limited precision. The second can measure each marble's position and velocity with ultra-high precision, yet still finite. Now, let's use these machines to reverse time, setting the velocities of the marbles with low precision, say to 2 decimal places, won't work. In a chaotic system with thousands of marbles, even tiny inaccuracies quickly accumulate, Precision to 2 decimal places is insufficient. Increasing the precision to 10 or even 100 decimal places still won't suffice. As long as precision is finite, reversing time remains impossible. In chaotic systems, any inaccuracy accumulates over time. To reverse time, infinite precision and information would be required. Thus, statistical systems can't return to their initial state, because from any present moment, there are infinite ways back. Moving forward, such systems seem to forget the path back. This concept, which Prigogine terms the entropy barrier, defines the irreversibility of time quite differently from the theories of Newton and Einstein. For Prigogine, the past is not only inaccessible, it simply doesn't exist. There is no past, although there was one. There is no past or future in our universe, but only the present, which is computed at every single moment. The profundity of this instantaneous nature of reality helps us to combine statistical physics with computation. Prigogine's instantaneous universe implies that the past is inaccessible because it is not computable at the micro level. Prigogine's entropy barrier prohibits the present from evolving into the past, except in the case of idealized systems like a pendulum or planetary orbits that look the same when moving forward and backward. Cesar Hidalgo. Now, let's delve into another physical aspect of information that is closest to us, the information we create with our knowledge and skills. Consider the products of our civilization through the lens of the information embodied in them and the subtle properties that arise from this. Life revolves around the constant processing of information. We are always in motion, engaging in various activities, whether we are driving, walking in the park, simulating virtual worlds, flying on airplanes, or exploring new experiences like tasting fried spiders. The world is vast and ever-changing. We strive to keep pace with it. Essentially, each of us is like a small, moving neuron within a large socio-economic system. We attempt to adapt and balance our personal desires with social life. It's a challenging endeavor, but it's the essence of life. We move, process information, and expand the volume of information through our actions in society. We create social structures to overcome our limitations, and these structures, in turn, learn to process information. This is how we generate information in objects and words. For society to accumulate information, 3 elements are necessary: an influx of energy, physical storage of information in solid objects, and our collective computational abilities. The sun provides the energy required to grow information on Earth. Plants convert this energy into sugar and subsequently into oil. Humans, however, have mastered the art of long-term information preservation, storing it in objects from the first stone axes to the latest telescopes and communication satellites. Building these objects demands not only energy, but also our distributed computational capability. Let's compare 2 types of apples: those that grow on trees and are sold in stores, and apple products from Silicon Valley. Both represent information, whether in biological cells or silicon chips. The primary difference isn't in the number of parts or the complexity of functions. Edible apples are the result of tens of thousands of genes participating in complex biochemical processes. The crucial distinction is that regular apples existed in the world before entering our minds, while Apple products like the iPhone or Vision Pro originated in someone's imagination before becoming a reality. Regular apples are packets of information, and Apple products are the fruits of human creativity. Cesar Hidalgo poetically refers to them as crystals of imagination. When we describe products as crystals of imagination, we mean they embody not only information, but also human creativity. This information is generated in our minds, and then manifested in physical objects. Edible apples existed long before we assigned them names, prices, and markets. They were a part of the world. In contrast, products like the iPhone and iPad were conceptualized in our minds before materializing in reality. Thus, the primary difference between natural apples and Apple products lies not in their physical order, but in the origin of that order. Imagination as a source is a fundamental feature of the information humans create and accumulate. For example, physicist Stephen Hawking. In the later years of his life, he was completely paralyzed and unable to speak due to a severe illness. However, a special device that detected the movement of his cheek enabled him to communicate with the world. This computer voiced entire lectures and scientific papers on his behalf. This illustrates a modern crystal of imagination, facilitating communication without voice or movement. Consider the cutting-edge brain-computer interfaces like Neuralink, which have been generating much buzz lately. Imagine a future where controlling a computer, typing, drawing, and playing games can all be done without moving a single muscle. In his book, The Fabric of Reality, physicist David Deutsch envisioned that such interfaces might one day enable us to create any virtual reality we can imagine. These concepts, which started as mere fantasies, are gradually being transformed into tangible devices. The creativity of scientists and engineers materializes in these technologies, providing humanity with revolutionary, almost magical capabilities. In the end, the economy is a collective system through which people accumulate information. Cesar Hidalgo. When we reflect on how products empower us, we gain a new perspective on wealth. It is our ability to encapsulate knowledge into physical objects that allows us to live far more comfortably than if we had to rely solely on our raw skills. Wealth, therefore, is intrinsically linked to humanity's capability to empower itself. Markets enrich us, not just with money, but with wisdom. They offer us access to the collective knowledge and imagination of others, accumulated over centuries. For instance, physicist Michael Faraday, who lived in the 19th century, discovered the laws of electromagnetic induction, without which modern electric generators would be impossible. He also invented the first electric motor, later perfected by Tesla. Thus, every time we use a blow dryer, a vacuum, or a blender, we are, in a sense, being assisted by Faraday, even though we have never met him, nor have our parents or grandparents. Economics, it turns out, is a system that transmits the knowledge and skills of geniuses like Faraday, Tesla, Edison, and many others to us. It's as if the spirits of these great scientists live on in every electrical appliance. Therefore, the objects surrounding us are not just inanimate things. They are repositories of knowledge, imagination, and skills of other people. This ability to embody knowledge in physical objects is not unique to humans. For example, ants can record information in their environment using pheromones. While an individual ant is not particularly intelligent, the colony as a whole can solve complex problems, construct intricate mazes, regulate ventilation, and find optimal routes. Humans do something similar, though not with pheromones, but by creating physical objects, from simple tools to grand structures like pyramids. It is this unique ability to translate imagination into tangible forms that has enabled us to build a society and economy far more complex than that of ants. But what is our ultimate potential? Where can the path of technological progress and knowledge expansion lead us? Physicist Max Tegmark, in his book, Life 3.0, articulates his thoughts on the potential of life this way. In my opinion, the most inspiring scientific discovery ever made is that we chronically underestimate the future potential of life. There is no need to limit our aspirations and dreams to 100 years of living in the midst of disease, poverty, and ignorance. On the contrary, thanks to advances in technology, life has the opportunity to flourish for billions of years, and not just here in the solar system, but throughout a cosmos far more interesting and vast than our ancestors could have imagined. This is extraordinary news for a species capable of accumulating information and pushing the boundaries of existence for centuries to come. Just as the Olympics push the limits of human physical abilities, science expands the frontiers of our knowledge and understanding, and art opens new horizons in the creation of beauty, enriching our experience of life. If technology can extend the limits of life as we know it, what are its true boundaries? How much of the universe could be suitable for life? How much matter could life harness for its benefit? How much energy and information can it extract? And how much computation can it perform? These ultimate limits should be determined not by our assumptions or logic, but by the laws of physics. Ironically, this perspective allows us to more easily comprehend the distant future of life than the near future. If we condense the nearly 14 billion-year history of the universe into a single week, the last 10,000 years of human history would occupy less than half a second. If future life remains as driven to push boundaries as current life, it will develop technologies and crystallize imagination to reach those final limits. But do we know for sure that future life will be so ambitious? Not entirely. It might become complacent and lazy. However, there is reason to believe that the drive to evolve is a genetic trait of advanced life forms, regardless of whether life aims for intelligence, longevity, cognition, or thrill. It will need resources, necessitating the development of technology to its limits and the exploration of the universe. It is plausible that life arises independently in numerous locations across space. In that case, unambitious civilizations will remain cosmically insignificant, while the most desirable parts of space will be occupied by the most ambitious life forms. Natural selection will operate on a cosmic scale, and eventually all remaining life forms will strive to evolve. Let's explore what we can achieve with the resources available in our solar system and what we can obtain through space exploration. For advanced life, the most crucial resource is baryonic matter, everything consisting of atoms and their particles. With the right technologies, baryonic matter can be transformed into anything: power plants, computers, or even living organisms. So, what are the limits on energy sources and computing power for advanced life forms? Any discussion about the future of life inevitably touches on concepts associated with theoretical physicist Freeman Dyson. Alongside Julian Schwinger and Richard Feynman, Dyson was a pioneer of quantum electrodynamics and other rigorous scientific theories. He believed that for a spacefaring civilization to achieve great things, it would need to maximize the energy extracted from its solar system. Dyson criticized the short-sightedness of humankind, pointing out that all our current energy needs could be met by harvesting sunlight from just 0.5% of the Sahara Desert's area. But why limit ourselves to only the energy the sun sends to Earth? Why not harness all of the sun's energy? In 1960, Dyson proposed the concept now known as the Dyson Sphere. This idea involves transforming Jupiter into a massive biosphere around the sun, enabling our descendants to utilize 100 billion times more biomass and 1 trillion times more energy than we currently have. Dyson envisioned that it would be a natural step for any advanced civilization to place itself in an artificial biosphere around its star. Living on the inner side of a Dyson sphere, the sun would always be directly overhead, and its light would pour from all directions, reflecting off the entire surface. To see the stars, one would have to climb to the sphere's exterior. A relatively simple way to create a partial Dyson sphere is by placing rings of habitable sections in orbit around the sun. For a full sphere, numerous rings would be needed at different distances and planes to avoid collisions. Building a monolithic fixed sphere, where the gravitational force of the sun is balanced by the pressure of its light, is another possibility. This sphere could be constructed gradually, adding more and more lightweight satellites, or statites. These statites would need to be extremely light, around 100 times lighter than paper. This is feasible, as materials like graphene are 1,000 times lighter than conventional materials. If the sphere primarily reflects light rather than absorbs it, the internal light intensity would increase significantly, inflating the sphere from the inside and allowing it to support more mass. For a heavier, more robust Dyson sphere, super-strong materials capable of withstanding loads 1,000 times greater than the foundations of skyscrapers would be necessary. The sphere would also need to be agile and intelligent, capable of adjusting its position and shape to allow safe passage for asteroids or comets through special openings. For present-day humans, life on a Dyson sphere would be extremely challenging, if not impossible. In orbit, there would be almost no gravity, and on a stationary sphere, gravitational force would be 10,000 times weaker than on Earth. Additionally, there would be no magnetic field to protect against solar radiation, unless artificially created. However, there's a silver lining. A Dyson sphere orbiting Earth would provide 500 million times more space than we currently have. If we desire Earth-like conditions in space, constructing cylindrical stations is a more feasible option than building a Dyson sphere. Physicist Gerard O'Neill proposed designs for cylindrical stations that would have artificial gravity, shielding from cosmic radiation, a 24-hour day-night cycle, and an Earth-like atmosphere and ecosystem. These stations could either orbit within the Dyson sphere or be attached to its exterior. The concept involves two large cylinders rotating in opposite directions to create artificial gravity through centrifugal force, similar to gravity on Earth. By keeping the cylinder's axes aligned with the sun and using special mirrors, sunlight can be directed to mimic Earth's day-night cycle every 24 hours. Additionally, a small cylinder around the station could be dedicated to agriculture. While Dyson spheres are incredibly efficient by our standards, they do not violate the laws of physics. Albert Einstein demonstrated that 100% conversion of mass into energy yields enormous energy, as described by the formula E equals mc squared. If we had abundant antimatter, we could achieve 100% energy efficiency. For instance, adding a teaspoon of antimatter to a tank of water would release as much energy as the explosion of 200,000 tons of TNT or a massive hydrogen bomb, enough to power the entire planet for 7 minutes. Unfortunately, our current energy extraction methods are highly inefficient. Digesting food uses only a trillionth of its energy. Coal and gasoline are slightly more efficient, and nuclear reactors harness less than 0.1% of uranium's energy. Even the sun's fusion process, which is 10 times more efficient, uses only 0.7% of hydrogen's energy. Stephen Hawking, in his book, A Brief History of Time, proposed using black holes as energy sources. While it was once thought that nothing could escape from black holes, Hawking showed that quantum effects cause black holes to emit radiation. Smaller black holes emit stronger radiation, but to harness significant energy, we would need black holes about 1,000 times smaller than a proton, and weighing as much as a cruise ship. However, creating such tiny black holes requires an accelerator as powerful as the Large Hadron Collider, and much of the energy would be lost in the process, making it inefficient. To make black hole energy extraction viable, we need a quantum theory of gravity, which we do not yet possess. Fortunately, there are other ways to harness black hole energy without quantum gravity. Many black holes spin rapidly, almost at the speed of light, and this rotational energy can be extracted. A spinning black hole has an ergosphere, a dynamic region just above the event horizon. If you throw an object into the ergosphere, it will be immediately picked up and swirl around the hole. But if you throw an object there at the right angle and split it in two beforehand, one shard will fall into the black hole and the second one will fly out with more energy than the object had at the beginning. This process allows us to extract some of the rotational energy from the black hole. By repeating this process, we can continuously extract rotational energy up to 27% of the black hole's mass if it is spinning at maximum speed. The supermassive black hole at the center of our galaxy has a mass about 4 million times that of the Sun. Even extracting 10% of its mass would yield energy equivalent to converting the mass of 400,000 suns with 100% efficiency, or the energy of 500 million Dyson spheres, in 1 billion years. There are other alternative methods of extracting energy from black holes without immersing them in quantum gravity. One such method is to harness the energy of matter as it falls into the black hole, as observed in quasars. Quasars act as cosmic power plants, converting the gravitational energy of falling matter into intense radiation that can be detected at great distances, for which they have been dubbed beacons of the universe. As the gas spirals toward the black hole, it forms an accretion disk that looks like a giant rotating pizza. The inner regions of this disk gradually fall into the black hole, causing the gas to heat up and emit bright radiation. The particles inside the gas accelerate, increasing their energy and creating chaotic motion. The intense heating results in powerful radiation, which can be produced by building a Dyson sphere around the black hole. The faster the black hole spins, the more efficient the energy extraction becomes, reaching 42% for the fastest spinning black holes. Another intriguing method of converting matter into energy without black holes is the Sphaleron process. Imagine a building set with two types of parts, red quarks and blue leptons. In a special configuration, red quarks can transform into blue leptons through an intermediate stage known as Sphaleron. During this transformation, the leptons weigh less than the original quarks, and the difference in mass is converted into net energy, reflecting Einstein's famous formula. The Sphaleron process represents a revolutionary way to convert matter into energy, without the use of black holes or complex quantum physics. Future advanced civilizations may develop a device called a sphalerizer, an energy generator that resembles a highly efficient diesel engine. While a conventional engine compresses a fuel-air mixture before ignition, converting mass into thermal energy, a sphalerizer would compress ordinary matter to temperatures of quadrillions of degrees, mimicking the conditions of the early universe. When the universe was in its infancy, 13.8 billion years ago, it was undergoing a similar high-temperature process, converting almost all matter into energy. Only a tiny fraction, less than 1/1000th, remained as quarks and electrons, forming ordinary matter. The sphererizer would be 1,000,000,000 times more efficient than a diesel engine and could be powered by any matter containing quarks. This high-temperature process in the early universe produced 1,000,000,000,000 times more radiation than matter. Over the past 13.8 billion years, a great stratification has occurred where atoms have coalesced into galaxies, stars, and planets, while photons remain as the cosmic microwave background between galaxies. Future evolved life forms could recreate this hot, dense state in the sphererizer, converting almost all matter in galaxies back into energy, briefly replicating the conditions of the early universe. To understand how effective the sphererizer is, it is necessary to understand some nuances. For example, how big should it be to minimize neutrino and photon losses during compression? This remains unclear. However, the energy potential is certainly far beyond our current technology. If our daily meals are 100 billion times less efficient than the maximum allowed by the laws of nature, what can we say about our computers? Surprisingly, the efficiency of our computers is even worse than that of our food. Massachusetts Institute of Technology professor Seth Lloyd, pioneer of quantum computing, claims that our entire universe functions as a quantum computer. He has demonstrated that the speed of computation depends on energy. He estimates that a kilogram computer can theoretically perform up to 5 times 10 to the 50th power of operations per second, 36 orders of magnitude, more than a modern laptop computer. Assuming performance continues to double every 2 years, we could reach this in a few centuries. Lloyd also suggests that a kilogram computer will be able to store up to 10 to the 31st power of a bit, 1 billion times more than today's laptops. He admits that even super-intelligent life would have difficulty reaching this limit, comparing the storage capacity of such a computer to the energy release of a hydrogen bomb or a fragment of the Big Bang. Nevertheless, Lloyd remains optimistic, believing that practical limits are not so far removed from physical constraints. Current quantum prototypes can already store 1 bit per atom. Scaling up this technology could yield 10 to the 25th degree bits per kilogram, 1,000,000,000,000 times more than conventional laptops. Using electromagnetic radiation to communicate between atoms could increase the speed to 5 times 10 to the 40th degree operations per second, 31 orders of magnitude faster than today's processors. These computational prospects for future civilizations are staggering. By comparison, a kilogram computer would surpass current supercomputers as dramatically as they would surpass the turn signal in a car, which stores a single bit and switches states about once per second. From a physics perspective, all future creations, from habitable zones and machines to new life forms, are essentially ordered elementary particles, or imagination crystals. Just as a whale is made up of ordered krill cells, and krill are made up of ordered plankton cells, our entire solar system is restructured. Hydrogen that has evolved over billions of years. Gravity organizes hydrogen into stars, which then produce heavy atoms. Gravity then organizes these atoms into planets, where chemistry and biology give rise to living matter. Advanced civilizations of the future will be able to rearrange particles much faster and more efficiently. They will use powerful computations to determine optimal methods and then implement them using available energy sources. We have already seen how matter can be converted into computers and energy, making it a basic necessary resource. When future civilizations reach their physical limits, the only way left to develop will be through space expansion, exploring the vastness of the universe. Compared to cosmic timescales of billions of years, the intellectual explosion lasts an instant in which technology reaches a plateau where it is limited only by the laws of physics. This technological plateau is located much higher than any current technology. If we continue to improve our technology with sufficient prudence, anticipating the consequences of possible mistakes so that we do not make them, terrestrial life has tremendous potential to flourish, both on Earth and far beyond for billions of years, beyond what the boldest of our ancestors could have dreamed of. Max Tegmark. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm.